This video is going to introduce the idea of stoichiometry. We're going to spend most of the time practicing problems because I think that's the most useful way of understanding and learning about stoichiometry. So if you look here, we have a chemical reaction. The coefficients in front of the molecules indicate the number of molecules that react to form the product molecules. So we learned that 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of liquid water. But another useful way of thinking about stoichiometry and the coefficients in front of the compounds in a chemical reaction are that not only can you think about it in terms of molecule ratios, but you can also think about it in terms of mole ratios. 2 moles of hydrogen will react with 2 moles of oxygen to form 2 moles of water. And this is sometimes a more useful way when we're using the reactions to do some stoichiometric. Now we've looked at this also. So molecular weight can be an atomic mass unit. So for example, a single molecule of water has a mass of 18 atomic mass units. That's a really small value. But a laboratory sized sample of water, if it is a mole, it has a mass of 18 grams. And so the molecular weight is either the mass of one molecule in atomic mass units, or it is the mass of 1 mole in grams. And then when you think about how many molecules are present in a mole, those are related by Avogadro's number. So 6.02 times 10 to the 23rd molecules or atoms or ions or entities or photons or whatever are present in 1 mole of whatever that sample is. We're going to do this practice problem in a few minutes to help people understand the relationship between mass and moles and molecules and atoms. Then we're going to move on and we're going to use this reaction, stoichiometry, to figure out if we have 10 grams of one reactant and an unlimited supply of the other reactant, not only how many moles of the reactant is that, or how many moles of oxygen are required to react with that much hydrogen, but also how many grams of product will form. So we're going to use the same value given to do a few different calculations. And then we're going to move on and we're going to talk about yield. And so yield is sort of how much product you make based on how much you could have made given the initial amounts of your reactants. So we'll do this calculation next. And I wanted to show you this flow chart. So whenever you're doing a stoichiometric calculation, you always have a balanced equation that you're going to use, and that's shown at the top in the green box. That's just a generic equation where the lowercase italicized letters are meant to be numbers. Those are stoichiometric coefficients, 1, 2, 3, 4, etc. And then the uppercase letters are meant to be reaction components, and so in the example that we're going to use, those would be hydrogen H2 and oxygen O2, and then the product was water H2O. So those are designated as the uppercase letters in the green box. So the flow chart at the bottom is meant to show you that if you're given mass of something like mass of A, and you're expected to go to something like mass of B or mass of C or mass of D, then the first step is always going to be to convert from the mass of component A into the moles of component A, and you're going to use the molecular weight or molar mass of A to do that. And then that second step, going from moles of A, you can go from moles of A to B or C or D. So you can convert from moles of any reaction component to any other reaction component simply using the ratio in the balanced equation, the stoichiometric coefficients in the equation. So the lowercase letters. So you would use those to convert from moles, between moles of any reaction component you want. In this example, they're converting from mass of one reactant into the mass of the other reactant. But you could also be converting into the mass of the product. So finally, if you're going to go from moles back to grams, then you again would use the molecular weight or molar mass of that particular sample. There's an example shown here from the book where, let's say you're given 1 gram of glucose, C6H12O6, and it undergoes combustion in the presence, oh no, sorry, that's not combustion. That should be combustion. It looks like that should be an oxygen. That's a typo, sorry. That should be glucose plus 6 O2s, not CO2s, are going to form 6 waters and 6 carbon dioxides. So if we have um, 1 gram of glucose and an unlimited amount of oxygen is what it should be, then the question is how much water would be made. And so in this example, you start with 1 gram of glucose, but they're trying to show you that you can't, that dash line at the top, no direct calculation, is trying to indicate that there is no way of going from mass of glucose to mass of water. That the first thing you have to do is convert from grams to moles of glucose, and then from moles of glucose to moles of water, and then from moles of water back to grams of water. So even though it's a complicated 3-step calculation, there's no direct way of getting from mass of one component to mass of the other. So molecular weight and molar mass are sort of two ways of thinking about the same thing. A single molecule of water has a molecular weight of 18 atomic mass units, or AMU. But then when you think about how that relates to a laboratory size sample, what that also means is that a mole of water weighs 18 grams. And so molecular weights can either have units of atomic mass units or grams per mole. And it just depends on how you're thinking about it. If you're thinking about the mass of a single molecule, then that's going to have a really tiny mass, which it would be in atomic mass units. Normally, however, the way we use these numbers mathematically is in lab-sized samples. And so probably a more useful way of thinking about molecular weight is as a molar mass, the mass of 1 mole. So we're going to do some practice problems here. You measure out 45 milliliters of water at 25 degrees. The density of water at this temperature is given here. How many moles of water is this? How many molecules of water is this? How many atoms of hydrogen are present in this sample of water? So we're going to start with A. And in this case, it's going to carry you through this. This is going to walk you through this calculation one by one. So we're going to calculate A, and we're going to use that to calculate B, and we're going to use that to calculate C. But sometimes I might ask you just to calculate C straight from the beginning. And so we'll talk about how you're going to know how to do that in multiple steps. But we're going to start with the first step. How many moles of water is this? Now, so we know the density of water and we know the volume of water. We need to use both of those values to determine the mass, because in order to figure out how many moles of water we have, we know that a mole weighs 18 grams, but what we don't know is how many moles this mass represents. And we don't even know the mass yet. We have to calculate that ourselves. So to get moles, we need mass. So we're going to combine 45 milliliters and the density. We're going to multiply them together so that milliliters cancels, and that gives us about 44.8668 grams of water. So that means that our 45 milliliter sample has a mass of 44.8668 grams. And to calculate part A, we're going to convert that into moles using the molecular weight. Water is composed of oxygen and hydrogen, so its molecular weight is 18.016. I calculated that by adding 16 to 2 times 1.008. So we're going to divide the mass by the molecular weight, and that's going to give me 2.490386323 moles, which has too many significant figures. The density has 5, the volume up here has 3, which means my mass is accurate to 3 significant figures, to this 8 that I underlined here. My molecular weight down here is accurate to the hundredths place because of the mass of water, 16.00, which means that my final answer should be accurate to 3 significant figures, 2.49 moles. Part B, we're going to use our answer to part A to solve part B. How many molecules of water is this? So we're going to start with the answer, the unrounded number that we had up here. To get from moles to molecules, we use Avogadro's number, which is abbreviated capital N subscript A. Avogadro's number is on your sheet. So this number here is a really long number. If you leave it in your calculator, like I usually do, you don't have to type it all back in again. It's best to use the unrounded number so that you don't get any rounding errors. But if you don't hit clear, resist that temptation to clear out your calculator at the end. This should still be in your calculator. Okay. So if we use this number, that's moles, and we multiply by Avogadro's number, and Avogadro's number you can find on the sheet. It is here. 6.022 times 10 to the 23rd molecules per mole. Moles cancel, and that gives me 1.4997 times 10 to the 24 molecules. Now it's a really big number, and it should be, because you should have a lot of molecules in 45 mils of water. So for sig figs, I know that my moles had 3 sig figs, and Avogadro's number from the sheet has 4. And therefore this is accurate to 3 significant figures, 1.50 times 10 to the 24th molecules. Part C, we're going to use our answer to part B. We're going to use the unrounded number, and we're going to use the formula for water, H2O. We're going to know that there are 2 hydrogen atoms in every 1 molecule of water. So we should have, what we should be doing is multiplying this number by 2, right? So if we have 1.5 times 10 to the 24th molecules of water, that means we should have approximately 3 times 10 to the 24th hydrogen atoms. We're going to use the unrounded number, which again is still in my calculator. There's my unrounded number, still in my calculator. I'm just going to multiply by 2. The molecules cancel, and that gives me 2.99942 times 10 to the 24. I need 3 sig figs. This number, this ratio of atoms to molecules is an exact number, 2 to 1. So that does not influence my sig figs. And so now we're going to round this to here, 3.00 times 10 to the 24th atoms. Now in this case, it doesn't look like you had any rounding errors, because the numbers that you rounded away, rounded down, were very close to the next digit. But you can influence your answer. Sometimes rounding errors will give you a different answer. And if it does, you would lose a point or half a point or 2 points or something like that, however much that was worth. Now this last question, you react 10 grams of hydrogen with an unlimited supply of oxygen. So if we have 10 grams of hydrogen, the first thing we're going to do when we want to go from grams to moles is we need the molecular weight. We're going to convert moles of A into moles of B using the stoichiometry. We're going to convert moles of B into mass of B using the molecular weight of B. This is an overall process that you're going to use anytime you want to go from the mass of one reaction component to the mass of a different reaction component. You have to first convert one component into moles before you can relate the two to each other. So they have to be in moles in order to relate them. So in this particular question, you're going to, just like before, you're going to use your answer to A to go on to B, and then use that to go on to C. In this particular case, so you're using the molecular weight to get A, the reaction stoichiometry to go there. Here, I'm kind of walking you through it on this first one, okay? But in the future, so I guess I just want to warn you that I won't always walk you through the problem the way I do here. Sometimes I'm just going to give you the mass of A and I expect you to tell me the mass of B, okay? So be prepared for that. Now here we're going to convert grams of hydrogen into moles of hydrogen by dividing by the molecular weight, which is 2.016 grams per mole. That gives me 4.96 moles of hydrogen. 3 sig figs and 4 sig figs in the molecular weight means my answer should be 4.96 moles of hydrogen. And since it asked me that question, I have to round it and circle it because that's the answer to part A, 4.96. But to answer part B, I'm going to use the unrounded answer to part A. And I need to go back and look at the reaction stoichiometry. So I'm trying to figure out how many moles of oxygen are required to react with this much hydrogen. And so I can see that there is 1 mole of oxygen required to react with every 2 moles of hydrogen. So that means that I take my moles of hydrogen, and this is the stoichiometric ratio, 1 mole of oxygen for every 2 moles of hydrogen. I put 2 moles of hydrogen on the bottom so that it will cancel with moles of hydrogen over here. So that's going to cancel and it's going to give me moles of oxygen. So I only need 2.48 moles of oxygen. I'm going to round that to 3 sig figs again and circle it, and that's my answer to part B. And finally part C, where you need to calculate the mass of water that would form. So we have our moles of hydrogen that were our answer to part A, but I'm using the unrounded number. This is the mole ratio of water molecules to hydrogen molecules. So it's a 2 to 2 mole ratio, or you could use 1 to 1. But this means that we would have 4.9603 moles of water and then we use the molar mass of water to calculate grams. Moles cancel, and that gives me 89.366 grams of water. I need 3 significant figures. The mole ratios are exact, so that means I need to round this to 89.4 grams of water. So this is my answer to part C. This video is an introduction to the concept of yield in a chemical reaction. So here I have my flask, and let's say I throw in some oxygen, and for fun let's throw in some hydrogen molecules as well, with the goal to make some water. And we're going to put a stopper on the flask, and we're going to see what we can make with that. And I'm thinking, I want to make some water. I'm going to make lots and lots of water. That'll be super fun. So, let's take a couple of molecules of oxygen and hydrogen, and we'll combine those to make water. You can see those here. So we've converted 2 oxygen molecules into 4 water molecules, along with 4 hydrogen molecules. And then I'm thinking, yeah, I'm going to make a lot. And then maybe there's another reaction that happens, and it's not one that I really anticipated. And I go, what just happened? I accidentally made something I didn't want to make, right? And so here, instead of making water, I made this other product. So this would be considered a side reaction. So unwanted side reactions are something that happen a lot in chemistry. And another problem is that sometimes the reaction does not go all the way to completion. So we often end up with some unreacted reactant left in the flask, right? So we have some oxygen here and here, and we have lots of hydrogen left over. So if we want to figure out how much we made, sort of our yield is related to how much product we actually got divided by the amount of product that we should have gotten if everything worked perfectly. If we had no side reactions, so none of this, and if all of our reactant react all the way to completion. So we're going to count the number of molecules we made. 1, 2, 3, 4. That's my actual yield. My actual yield in this case was 4 molecules. Now if we think about how many we could have made, the theoretical yield is maximum possible yield from the starting material. So if we think about the starting material that we had, right, we have these oxygen atoms, these oxygen molecules. So we're going to include the 4 we did make. Those are certainly ones we could have made. And then we're going to add to that the ones that never came to be, right? And so there's an oxygen molecule here that if we combine that with 2 hydrogen molecules could make 2 waters, right? So there's 1 water molecule there, and there's another possible water molecule there. So over here, this O2 and 2 H2s could have made 2 more water molecules. And then here's another potential water molecule over here in the bottom right. And then here I have this oxygen left over and another H2 up here. Those could have combined to make a water. And then the side reaction that happened, if that hadn't happened, and instead I had had the correct product of an H2O, that would have been an H2O, and then there's an extra oxygen atom there. If he had combined with one of these hydrogens up here, then that's another possible product. So if we think about the theoretical yield in the picture I have here, the 4 that I did make count, plus 5, 6, over here, 7, 8, plus this mistake product, 9, plus up here, 10. So it seems like there are 10 possible water molecules that could have occurred, could have been produced based on the things I circled in blue. So I think that's a 10. I think there are 4 that I made and 10 that I didn't make. And then I have 2 extra hydrogen molecules. So if I add them all up, 4 actual and 10 theoretical, That gives me a yield of 40%, which isn't really that great. And we're going to move on, and we're going to do this practice problem where we have 10 grams of hydrogen and an unlimited supply of oxygen. And we're going to form 65.7 grams of water and figure out what the yield is from that. So if we have 10 grams of hydrogen and an unlimited amount of oxygen, that means that the hydrogen is the only thing that limits how much we can make. So if we figure out from the mass of hydrogen, we're going to start with how many moles of hydrogen that represents. And then we're going to convert that into moles of water using the stoichiometric coefficient 2 to 2. Then we're going to convert that into grams of water, and that's going to tell us the maximum possible mass of water that we possibly could have formed. It appears that it's 89.365 grams. So based on the 10 grams of hydrogen at the beginning, if all 10 grams react and form nothing else but water in an unlimited amount of oxygen around, and all the hydrogen reacts completely and there's none left over, then we should get 89.365 grams of water. So your theoretical yield is here. It is based on the initial mass of reactant. The value that's given in the problem, 65.7 grams, is the actual yield of water. That's what you actually made. So this is the theoretical yield, 89.365. The actual yield is 65.7. The percent yield is the actual yield divided by the theoretical yield times 100. So if you plug those numbers in here and multiply by 100, then you get 73.51865, which has too many significant figures. If we go through and figure out how many significant figures there should be, the number 10.0 has 3 sig figs. The molar mass of hydrogen has 4. The stoichiometric coefficients are exact. The molar mass of water has 4, which means that my theoretical yield is accurate to this 3, so that has 3 sig figs. My actual yield given has 3 sig figs, which means my answer should round to 3 significant figures. The number 100 is exact. So I end up with 73.5% as my answer.